So today we're starting Unit 3, Spatial Sense, working in geometry, our shapes. Lesson 1 is classifying polygons. As I've already said in this class, the majority of this is review, but some people may have forgot it, or maybe over COVID you didn't really cover it. I don't know. But we start with two questions. First of all, what is a polygon? And two, how do we classify it? So our first part, right? What is a polygon? What is a polygon? What do we have as the answer? What is a polygon? Anyone remember?
A square.
A square is a type of polygon, yep.
Any geometric shape.
Yeah, we say any 3 or more closed sided shape, right? That's where we start. We can't have a two-sided shape because that's a angle, right? Close it off, 3 sides, 4 sides, 5 sides, right? 6 sides, we can continue. You get the idea, right? Any 3 or more closed-sided shape. That's what we've been taught. That's kind of what we think of for the most part, right? We say that two sides will meet at a vertex. What's a vertex?
A point.
Yeah, so two sides are meeting at a point. When we just have angles, we still have two sides meeting at a point. But in a closed-sided shape, you can't have things like this, right? Because we've got something open here, right? You can, however, have them connect like that, right? So you have to have two sides meeting at a vertex. And we also say the sides only intersect at vertices. Okay? So they're not intersecting anywhere else. Question. Is this a polygon?
No.
Is this a polygon?
Mm-mm.
Why are we saying no?
It's not closed.
Yeah, it is. Oh, no, it's not.
Where is it not closed?
It's not closed on the right.
What about this? Polygon?
No.
Why is this not a polygon?
It's not closed. Yeah, it is. Not fully.
You say it's closed, Georgia? You say it's not closed. But what about this? Are the sides only intersecting at vertices?
No.
No.
Well, what's this?
That's a,
Because that becomes an issue for us in this, right? This is the problem, is that you're really combining two polygons together in one, right? So it's not actually considered a polygon, because this line segment here, or side, ends up intersecting and going through as opposed to stopping at a point as a vertex. Okay? So when we have those intersecting lines, it lets us know it's not an actual polygon. All right. So that's the first question. What is a polygon? Right? And second question was, do you remember?
how do we classify it?
Yeah, how do we classify it? I hate to bring this up, but we've been talking about classification a lot this year already. We figured out about how we classify literature. We talked about genres. But we also classify shapes and polygons. Yeah?
The sides, vertex, and vertices.
Yeah, so here's some of them. Right? 1. let's not put this arrow. Let's go like this. 1. Sides. We can classify by the number of sides, right? So we'd say a triangle equals 3 sides. And we could say a quadrilateral equals 4 sides, right? Pentagon 5. What's after a pentagon? Hexagon.
Decagon.
Decagon is 10 sides.
Yeah.
Septagon,
Septagon, yeah.
right? Octagon, right? So as we go up, we can classify by the sides that we have. That's one of them, okay? I'm going to bring this second one over here so that we've got more room. I think you said this, but we also classify by angles,
Yeah.
right? So when we talk about angles, we can talk about, well, what are some of the angles that we understand? We know that there's an acute angle,
Acute.
right?
Right.
There's a right angle.
Obtuse.
We have obtuse. We have a straight angle, right? And you may or may not, but there's actually, we classify some of these polygons by what we would call a convex polygon and a concave polygon. Show of hands, how many people have heard of a convex polygon or a concave polygon? Anyone want to take a guess at what they mean? Yeah?
In and out. Out and in.
Out and in, yeah.
Concave means out. No,
Concave,
means
convex,
Concave means end, so
Concave
a
means-
polygon
an inward polygon.
an inward polygon, okay. With a convex polygon, all angles are, what do we think?
Out. Obtuse. Obtuse, yeah.
Obtuse? What's an obtuse angle again?
Larger than 90 degrees.
Larger than 90, but less than
360.
less than 180,
Okay.
which it would technically be less than 360, yeah. That's what we're saying. But this one says all angles are less than 180 degrees. Okay? So all the angles have to be less than 180. Less than a straight angle. Okay? With a concave polygon,
So it has to be more than
at least one
80, yeah.
angle more than 180. Right? So you might say, Mr. McCourt, I have no idea what that looks like. And I might say, well, let's say you had something like this. Right? This angle here
Concave.
is a concave angle. It's more than 180. Because we know 180 is a straight angle, right? So this one here is more than that. So this becomes a concave polygon. A concave polygon, okay? So we classify by sides, we classify by angles. Is there any other ways we classify?
Number of vertices.
Yeah, that's kind of the same as angles,
Yeah.
right? But yeah, so I might just throw that in here too. 5 vertices. Okay? We also classify whether or not something is regular. What does that mean? If we have a regular polygon. If it's regular, it means all sides
Are the same length.
are equal and all angles are equal. Okay? So all sides and angles are equal. It becomes a regular polygon. Okay? We also sometimes classify by what we call line symmetry. Okay? What is line symmetry? What is line symmetry on a polygon? What is line symmetry on a polygon? Let's put up a really simple polygon, let's say. Okay, let's pretend my artistic drawings will not be fantastic. But let's say this is an equilateral triangle. And we remember that we can know it's an equilateral triangle because we would mark that all sides are equal. Jess?
It must have one line of symmetry.
It must have one line of symmetry. And all the angles are equal. So we know that, right? When we have a line of symmetry, that means, right? We explain symmetry saying that it can be, the polygon can be divided into two equal parts. Now, it's like you're dividing it in half, and if you were to fold it over on itself, would it fit perfectly? Now, when we look at something like this, let me see, red will show up hopefully. I know that if I was to cut this down the middle, may not look great because I didn't actually measure it out, but if I was to fold it on itself, would it fit perfectly? Now, if this was a regular triangle and all sides and everything were equal, this would have line symmetry, right? But how many would it have? How many? Well, I can see one right here, sure. Is there any other forms of line symmetry?
Yeah. Yes.
How many?
2.
2 more? Where would they go, Josie?
You would fold it half and then fold it over again and then fold it over again.
Like if I put a line through here and folded it down, would it work?
Maybe only if you folded it like this way first.
Huh. Are there any more line symmetries through here?
Technically, no. If you fold it, if you
yes,
already
but-
fold it, then no.
What if I don't fold it and I just leave it like that?
There's 2 more diagonally.
There would be at least 2 more. Because we know this
Oh.
goes from a vertice through the middle.
There, yeah. I knew there was something.
We could go there, and we could also go
There.
here, right? So it actually has 3
Line symmetry.
3 ways in which we could cut it through line symmetry. So we can classify polygons that way. And we could say there is line symmetry, it has this much line symmetry, okay? So if we cut it in half and we fold it, would it fold over perfectly on each other? That's how we explain line symmetry. If I was to put one through the middle and fold it down, it's not gonna fit. But line symmetry is often associated with, when you're looking at regular polygons, vertices. See how we started the vertices and we are able to cut it in half. There's a connection between the numbers of lines of symmetry and the vertice on a regular polygon. Now, you can have irregular polygons that also have lines of symmetry. We could have something like this. And we could say that has line symmetry, right? Because I could fold that down on itself. I could also fold it over on itself. And this rectangle could have 2 lines of symmetry. Could I do this?
No.
No. Could I do this?
No.
No, it's not going to work, right? So this rectangle would have 2 lines of symmetry. Okay? The very last thing that we're going to talk about, and the last way of classifying, number 5, I'm going to have to get down here to do it, is what we call rotational symmetry. Rotational symmetry is explained as, could a polygon rotate around and still appear the same. Okay? Can a polygon rotate, I might say, equally on itself? And we also, I'm going to write this here and underline it, we use the term order to explain rotational symmetry. Okay? It's a little bit weird, but I'm going to use my same equilateral triangle that I have up here. And we'll talk more as we go through about some of these things, but rotational symmetry looks like, let's see if I can do it somewhat equilateral-ish. So rotational symmetry says, could we, from the middle, rotate our polygon and the shape fit inside itself? And how many times could we rotate it to get it back on itself? So oftentimes what people will do is they'll like put a dot in a corner, right? And if they have like tracing paper or something, they'll put it on top, they'll draw their shape, and then they'll rotate it, okay? So if we were to rotate this, how many times would we have to rotate it to get back into its actual spot here? So if I rotated it and my dot goes up to the top, that's 1. Then I rotate it and it still fits, and my dot's over here, that's 2. Rotate it one more time and the dot gets back, that's 3. So we say that the rotational symmetry of this equilateral triangle is order 3. The rotational symmetry is order 3. And we can rotate it around. Now, if this isn't a regular shape, meaning all sides and angles are equal, could you still have rotational symmetry? I mean, it's possible, because you could have something like I had up before, and you could have something like that, and you could rotate it. Now it's way up here, so it doesn't work. But you could rotate it again, and then that dot would be up here. Then you rotate it there, and you rotate it back. So it could have rotational symmetry order 2, right? It would fit in twice to get through. But we have to be careful when we're looking at rotational symmetry and understanding how it works, right? How we rotate it around that center point. Most of the time when we're talking about rotating objects, and we're talking about transformations, we're usually picking a point outside a shape. Sometimes it goes inside, but most of the time it's outside. Okay? So those are the ways we classify polygons. We know polygon to be a 3 or more close-sided shape. It must meet at vertexes, sides, and they intersect only at vertex. We classify them by how many sides they have, by the types of angles they have, or the number of vertices, whether or not it's regular, the line symmetry that it has, or the rotational symmetry. These are all ways in which we can classify. We're going to go through and we're going to work on some practice on those.